Before I start, I'd like to acknowledge the first author of this presentation, Ryan Tice. He's one of my graduate students in my group, and he did all the experiments and analysis in this presentation. And in this talk, I would like to talk about the challenges in controlling methanogens in microbial electrolysis cells. So I'm pretty sure everyone is familiar with the concept of a microbial electrolysis cells, or MECs. In MECs, there's bioanode and cathode. At the bioanode, organic substrate is oxidized to carbon dioxide, and at the cathode, water is reduced to hydrogen gas, so that we can achieve energy recovery in the form of hydrogen gas, and also we can achieve wastewater treatment simultaneously. And energy requirement for hydrogen production, especially through electrolysis. This is an abiotic water electrolysis cell. So at the anode, water is oxidized to oxygen, and at the cathode, water is reduced to hydrogen gas. In this system, the voltage requirement is 1.3 volts. But if you look at the MEC system, when the organic matter is oxidized at the bioanode, then the energy requirement is just 0.14 volts. So in typical MEC systems, the recovered energy as hydrogen gas is usually greater than the provided electricity energy. So we can achieve energy efficient hydrogen production. So like I mentioned, if you have MEC, we can achieve efficient hydrogen gas production. And MEC has relatively simple reactor configuration, so we need only bioanode and cathode. And we don't need any kind of aeration systems, so we can easily scale up MEC systems. And also, if you look at the rate of reactions in MECs, we can easily achieve, not easily, but we can reasonably achieve 1,000 amperes per cubic meter, which is equivalent to 300 milligrams of COD per liter per hour, which is quite comparable to conventional activated sludge systems. So if you use MECs, I think MEC is almost very ready for practical applications for wastewater treatment and simultaneous hydrogen gas production. And there's one challenge, which is methanogenesis over here. If you produce hydrogen, hydrogen is rapidly converted to methane, but through the hydrogenotropic methanogenesis. Hydrogenotropic methanogens use hydrogen gas as electron donor, and they use carbon dioxide as electron acceptor and carbon source, and they produce methane. This figure shows the rate of growth of microbes. So here y-axis is the microbial population at a given time divided by initial microbial population, and x-axis is the time. So if you look at, and there are two types of methanogens. One is acetylcholastic methanogens who use acetate and convert acetate into methane. And over 4 days, they multiply their population by about 3 or 4 times. But if you look at the hydrogenotropic methanogens, after 4 days, your reactor, the microbial population is going to be multiplied by more than 10 million times. So we have to do something to control hydrogenotropic methanogens. So in lab scale experiments, we typically use 2-bromoethane sulfonate, or BES, to control methanogens. But this is not an option in practical wastewater treatment. And since methanogens are strict anaerobes, so if you use air exposure or aeration system, you can control methanogens in the system. And in previous studies, they use air exposure and aeration, but in this case, you need aeration system. So in our study, we kind of developed a in situ oxygen generation system using pure oxygen generation system using abiotic water electrolysis, like applying voltage greater than 1.23 volts, we can induce oxygen generation at the anode. So this is the 3 electrode MEC that we developed. Please don't get distracted with the complicated circuit out there, but the bottom line over here, we have 3 electrodes. Electrode 1, or E1, is the bioanode, and electrode 2 and electrode 3, they are abiotic electrode made out of the stainless steel mesh. And during the normal operation, Just like MEC, bioanode is connected to the positive end of the 0.8 volt power supplier, and the electrode 2 and electrode 3 is connected to the negative end of the 0.8 volt power supplier, so that we can produce hydrogen gas at electrode 2 and electrode 3. And during oxygen operation, this bioanode is disconnected from the circuit, and electrode 2 is connected to the positive end of another power supplier that is set at 3.5 volts, and electrode 3 is connected to the negative end, so that we can produce oxygen at electrode 2. And we built 4 different MECs. MEC1 is the negative control, so it doesn't have any oxygen production here. MEC2, we produce the oxygen for 5 minutes every 12 hours. In MEC3, we produce oxygen for 15 minutes every 12 hours. In MEC4, we produce oxygen for 15 minutes every 6 hours. So MEC2, the least amount of oxygen production, and MEC3, a little more, and MEC4, a little more and more frequent oxygen generation. So detailed method, we operate reactors at fed batch mode, and each batch cycle takes about 3 to 4 days. And for the feed solution, we started from 50 millimolar phosphate buffer solution. We added 1 gram per liter of sodium acetate, and we added 1 milliliter of the methanogen inoculant from control MEC. And we also added some certain amount of bicarbonate, because with hydrogenotropic methanogens, they need carbon dioxide as the carbon source and electron acceptor. And electrode 1 was made of graphite fiber brush, and electrode 2 and 3 were made of the stainless steel mesh. And we didn't use any platinum or expensive metal catalyst. Here's the result. So this is the gas analysis results for methane. So y-axis is the methane volume in milliliters to 10 milliliter, and x-axis is the fed batch cycle from 1 to 9. And if you look at MEC1 over here, which is a circle, it started producing very quickly in cycle 3, and it increased, and in the end, it is dominated by methanogens. And if you look at the MEC2, which is denoted as triangles over here, there's no methane up to cycle 4, but it is dominated by methanogens in the end. And if you look at the MEC3, it is better controlled up to cycle 5 or 6, but in the end, it is also contaminated by methane. And MEC4, minimal amount of the methane up to cycle 9 or for a month. But in the end, at cycle 10, the methane jumped, and then it is eventually contaminated by methanogens. So it is not that good. And if you look at the control reactor, at cycle 9, we started producing oxygen. So you can see certain drop of methane in the control reactor, and then it stays a little low for 4 cycles, and then it went back up to like 6 or 8 milliliters of methane. And this is the oxygen volume. So y-axis is the oxygen gas volume in the collected gas up to 20 milliliters. And I'm going to start with the MEC1, basically 0 oxygen there. But at cycle 9, when we started oxygen operation, there's a slight jump in oxygen gas. And this is MEC2, it is consistently low. And MEC3, it was high for the maybe 4 or 5 cycles, and then it is getting lower. And same thing for the MEC4, it is the highest, up to 80 milliliters of the oxygen, but in the end, it dropped. And especially if you can see a little difference over here, when the reactor was dominated by methanogens, the oxygen concentration rate was basically dropped from 2 to below 1. Anyway, so in the end, after 1.5 months of operation, all the MECs were dominated by methanogens, so which is not good. So we opened one of the reactors, and we found there are a lot of biofilms. This is the bottom of the reactor, the black biofilm, thick black biofilm on the bottom of the reactor, and this is the gas collection port, and there are a lot of biofilms. So we we prepared 2 hypotheses. The first one is that these are aerobic biofilms. They rapidly produce oxygen. So there is no oxygen that can control methanogens. And in the second hypothesis, we were thinking maybe these are Methanogen biofilm. So this Methanogen biofilm protects active methanogens from oxygen. And especially we are kind of concerned about this black biofilm, Methanogen biofilm on electrode 3. So this is the clean electrode 3, stainless mesh, and this is contaminated electrode 3. So if you look at the electrode 3 during normal operation and oxygen operation, it is always producing hydrogen. So it has minimal exposure of oxygen. So we are thinking that electrode 3 is working as a refugee of methanogens. So we kind of developed a new operation scheme. So at step 1, it is same as the normal operation like MEC. Step 2, oxygen production at electrode 2. And step 3, going back to normal operation. And step 4, we produce oxygen at electrode 3 so that we can control, well, we can kind of deactivate the thick Methanogen biofilm on electrode 3. And here's the results. The methane volume, and here's the start of the alternating oxygen generation between electrode 2 and 3. So there's a slight drop, and then it went back up. So it is not really working. So basically, no improvements in methane control. But the electrode 3 was kind of completely cleaned right after this alternating operation. So kind of, we are thinking that, yeah, our second hypothesis, yeah, we did have Methanogen biofilm, but they were not the main reason why we weren't able to control the methanogens. So we went back to the first hypothesis. The aerobic biofilm in MECs, they consume oxygen really rapidly, so that we have, at the end of the day, we have limited control of methanogens. So we went back to the gas analysis results. So we collected all the data points over here, and then we plot these data for methane volume fraction in percent as a function of oxygen volume in the gas analysis. And then we found this clear negative correlation between methane volume fraction and oxygen volume. And we also found that there is a threshold oxygen volume, like about 2 or 3 milliliters, where we can control methanogens in this direction, but if the oxygen volume is smaller than this threshold the amount, then the methane control was not really good. So bottom line is that the aerobic biofilms consuming oxygen are responsible for the limited or failed methane control. And let's have a look at the oxygen sensitivity to the bioanode or exoelectrogenic bacteria. So here, y-axis is the average current in milliamps. So we average the electric current over maybe 6 or 12 hours when the bioanode is active. And then x-axis is the fed-batch cycle. So if you look at MEC1 over here, it is high around 3 milliamps. This is MEC2, about 2/3 of the control. And if you look at MEC3 and 4, they're about half of the electric current in control reactor. And I also want to mention that when we studied oxygen over here, there's a drop in electric current from kind of 3 to about 2 milliamps. So there is some negative effect of the oxygen production to the bioanode. So in conclusion, methane was better controlled with longer and more frequent oxygen operation. And from the correlation between methane and oxygen volume, a threshold oxygen volume was found for the better control of methane. And anaerobic biofilms made it difficult to kind of control methanogens because those biofilms quickly depleted oxygen. And Methanogen biofilm have relatively minor effects on the methane control method. And electric current reduced with oxygen generation by about 30 to 50%. And I'd like to thank all of my kind of group members, Ahmed, Joseph, Mohammed, Ryan, Wendy. And I would like to thank our lab technician, Anna Robertson, Peter Kudis. And I would like to thank the Faculty Startup Fund from McMaster University and Discovery Grant from NSERC. Thank you very much.
So we have time for a few questions. considered varying the pH or as a means to control the pathogens?
We didn't test the effect of pH, but there is a research paper that tested the low pH as a method to control methanogens, but it was not very effective. And if the pH is below 5, yeah, he's basically inactivated by
Heavy.
So kind of low pH may not be good.
Any other question?
I have a question about your anode. When you switch from cathode to anode, you're applying 3.5 volts, but do you know what potential your anode is and what products you're generating? You could be generating, if you're generating ozone or passivating your chromium layer or absorbing corrosion.
Yeah, there might be other oxidation reactions at the anode, but the majority of the reaction will be the oxidation of water because the water is kind of 90% of the content in the reactor. So we assume that the oxygen evolution reaction is the most dominant reaction at the anode, at the electrode tube.
So one thing could be that you're fouling that layer by direct oxidation of organic matter that's in solution, that's passivating your anode, like you're generating a polymer layer on that anode. So maybe that drop in oxygen isn't necessarily from scavenging, but from losing your...
Are you talking about the biofilm on the electrode 3?
No, on your oxygen generating elements.
Oxygen generating?
Yes.
Since it is kind of bare thin mesh, so I don't really think
You're not
there's...
seeing any drop in current as you apply the potential.
No, current was kind of quite consistent. Okay, when you apply the volts, current was quite consistent. We're going kind of 15 or 5 minute time period. So there's no fluctuation in the current data.
All right, if there's no more questions, let's thank the speaker one more time.